Hey chemistry students, I'm on page 92 and this is chapter 3, unit 2, and we're talking about how we discovered the atom. Discovered its structure, discovered what it looked like, what it's made up of, and I'm going to use a timeline. So on this timeline, I'm going to have the time, scientist, and what the scientist's idea is. All right, I'm going to try and summarize it. Way back in 450 before the Common Era, Democritus said that all things are made up of atoms. It's the smallest structure. If you kept cutting it and cutting it and cutting it, you'd get an atom. And Aristotle, just for the record, disagreed. He thought that all things are either earth, air, water, or fire, or a combination of all of those. A guy named Dalton, this is the same. These are Greeks at around the same time. Dalton in 1803. We're getting closer to the Industrial Revolution now. Dalton, we have he confirmed that all things are made up of atoms, but he added to it that there are different types of atoms, and they combine to make up all of the variety of matter that we have on the planet. So we only have about 90 occurring elements, but they combine, and that's what makes up the variety of matter that you see today. Right? But atoms, we didn't know what they looked like at this time. They're like marbles. Right? They just look like marbles at this point. We have no idea what their structure is, what they're made up of. Atoms just look like little solid balls. Right? Well, we're trying to slowly discover this, and we have to honor Thomson's contribution. J.J. Thomson, he studied electrons. And he studied electrons using something called a cathode ray tube. And basically this cathode ray tube is a flow of electrons. If you have a negative post and a positive post on a strong battery, say this is negative and this one's positive and this is wired up. This is a positive end, and then you have a flow. You have a nice flow of electrons. Well, he didn't know what they were. He didn't know their charge or anything. So what he would do is he would study this by putting a magnet along here, let's say, and with that magnet he noticed that because the electrons were attracted to the positive end and they flowed closer to that magnet, he concluded, accurately I might add, he concluded that these elements have subatomic particles. And he called them electrons. He knew that they were negative. And by the way, this is called a cathode ray tube. So he's known for doing his work using a cathode ray tube. All right, but he didn't know what they looked like yet. And so his idea was that atoms are a mix of positive and negative. And this is what's referred to as the plum pudding, because it's just positive, negative, all randomly blended together. There's no area for negative and area for positive. All right, so that's not accurate, and I don't want anybody to think that's accurate. But for J.J. Thomson's time, it was the best they had. All right, the plum pudding is a term that comes up quite frequently. It's the first step in discovering the structure of an atom, and for its time it was forward thinking. However, we now know it was inaccurate. Okay, so let's continue with our timeline. And 1909, Rutherford. He knew that there was negative charge, because we know about Thomson. So there must be a positive. There must be a positive as well. And so he conducted experiments. He conducted experiments with alpha particles. And an alpha particle is the best way to describe an alpha particle, and this just means alpha. An alpha particle is 2 protons, and those are 2 positively charged particles, and 2 electrons, and those are negatively charged particles. And so that's what an alpha particle is, and we get them as a result of nuclear decay that we'll find out later. So they knew about radioactivity, and this nucleus was decaying. So he was able to generate these alpha particles. Of course, today we would say this is radioactivity, very, very dangerous. At the time they weren't quite. They didn't quite know what they were doing. But anyway, here's a piece of foil, and he happened to use gold because you could hammer it out extremely thin. And so what he did was he shot this foil with alpha particles. When he shot this foil with alpha particles, what happened was most of them went right through. And so, well, an atom just must be empty space. But every once in a while, they would deflect. And then he kept, as a matter of fact, it was one of his students, kept shooting it and moving it around. And once not very often at all, extremely rare event was it would come back. And his student, this student just thought that was fascinating. That why would it come back? Because most of the time it just went right through. And so what that did was, by the way, this is called the alpha scattering experiment. Because they're shooting alpha particles, which, as I said, are just a helium nucleus, and they're going straight through the foil, which means that it's empty space. And so, really, what was going on today we know this, of course they didn't know this at the time, is that there was this dense core that we now call the nucleus, and these alpha particles were essentially just barely missing this nucleus, but every once in a while it would graze it and then of course get deflected, but then it would hit it and then come back, and that's whenever he discovered that there must be a nucleus. Therefore, elements have a nucleus. So, great test question. Who was it that first proved that there was in fact, a nucleus the elements have a nucleus? Rutherford, of course. Rutherford is responsible for that. Right? And how did he do it? He did it using his alpha scattering experiment. He shot some gold foil with some alpha particles, and they came flying. So they came flying back. Now, this story is not finished. This story goes on because we now have in 1912 a gentleman by the name of Bohr, and he argued that electrons are in energy levels. All right. Electrons are in regular energy levels. They're not revolving around the nucleus like planets. That's what Rutherford thought. Rutherford thought that they were going around like planets. Here's some models, typical test question. Which of these models best illustrates our current understanding of subatomic particles? Well, you have a dense core and then electrons in electron clouds or energy levels. Here is that plum pudding where they're randomly distributed in a core. Here they look like planets revolving around a sun, which we know is not the case. And this is what we call a distractor. This is just an image that doesn't apply at all, right? Bohr is responsible for our final best model of the structure of an atom.